Hey everybody, welcome back. Thanks for watching. As promised, we're going to compute the antiderivative or indefinite integral of secant of theta d theta in three different ways. So the first way is sort of the classic way you might show a Calc 1 class. When I was a student, I remember thinking this was sort of maybe the least satisfying because it seems like this just pops up out of nowhere. You have to have some sort of just mystical insight to arrive here instead of computing it. But I remember what we did was, and this is sort of the classic way to do this, was to multiply by this useful form of 1. And I remember again as a student, where on earth did this come from? How did someone think to do this? Now I understand you can sort of reverse engineer this from the derivative once we compute, but again, seeing this for the first time is sort of perplexing. Okay, and then you just multiply through and do a substitution. So if I multiply through, the numerator is going to be secant squared of theta plus secant of theta times the tangent of theta. And then the denominator, because again that's over 1, that's going to be secant of theta plus tangent of theta d theta. And now typically we will let u equal the denominator. Let's see if I've got enough room for du. Always an adventure. So that's going to be secant of theta plus tangent of theta. And so du is going to be secant of theta tangent of theta plus secant squared of theta. Now that's d theta. That gives us the classic du over u form. Of course, we recognize that as a natural log form. And then we back substitute. Okay, so yeah, that's method number 1, sort of the classic way that's shown in Calc 1, maybe even Calc 2. I prefer the second way because you directly compute it. So this one, again, you have this sort of amazing, magical, mysterious factor that just emerges from some sort of insight. But for the next one, like I said, we're going to directly compute. Okay, let's see what's going on in our second computation of the integral of secant. So we can write this as, just by definition of secant, 1 over cosine of theta. And we're going to multiply the top and the bottom by cosine of theta. Now, I guess you could make the argument, where did that come from? But if you think about it, it seems maybe a bit more natural because this would introduce a Pythagorean identity. So that seems pretty reasonable. And from there, you can do a substitution. So for me, at least, this makes a little bit more sense instantly. So by Pythagorean identity, the denominator can be rewritten as 1 minus sine squared of theta. And then we'll just proceed with a substitution. So we're going to let u equal sine of theta. That makes du cosine of theta d theta. And so here I've got this classic rational function. We're going to proceed using integration by partial fractions. Okay, so we're going to sort of put the calculus on hold. We're going to work with partial fractions. Let's go ahead and factor the denominator here. So that'll factor into the product of conjugates because that's the difference of perfect squares. And that'll decomp into a constant over the first factor plus a constant over the second factor. Okay, we're going to multiply through by the least common multiple of the denominators. So that's 1 minus u times 1 plus u. That gives me a nice statement without fractions. And forms like this are pretty nice. These arrive from these, linear unique factors. This is nice because this equation right here is true for all u, so that means it's certainly true for well-chosen u. So, for example, if I choose u to be 1, this term will drop out. That'll allow me to solve for a. So if u is equal to 1, of course I plug that value in for all u. That forces a to be a half. You can check that. Well, if I want a to drop out so I can solve for b, if u is equal to -1, that will drop out. I can solve for b. So in that case, b is also 1/2. So that means I can take this and I can write this as the integral of a sum of two fractions. So in some sense, this is sort of like common denominators in reverse. Instead of adding two fractions together, you're sort of ripping them apart in this systematic way. So again, that means that this is equal to, now both a and b had 1/2, so I'm going to factor that out. So that means I've got 1 over 1 minus u plus 1 over 1 plus u. So again, plug a in for a, b in for b. But both numerators have the 1/2, so you can factor out in front. And that's du. And so next, I'm noticing a natural log for both. So here I'm going to get a negative ln of absolute 1 minus u. Here plus ln of 1 plus u. And the negative, of course, is because of the coefficient of u. Okay, so I'm feeling pretty good at this point. I mean, we've done the integration. Now we want to do some back substitution and a bunch of algebra. So by properties of logarithms, so we know that ln of a minus the ln of b is equal to the ln of a over b. And so I'm just going to rewrite this so you can clearly see the negative in the middle there, so it's not hanging. Okay, so yeah, I've got the difference of logs, so I can write that as the log of a quotient. And so also in terms of absolute values, we know that the absolute value of a over the absolute value of b is equal to the absolute value of a over b. So that means I can write these individual absolute values as a single absolute value. So I've got 1 plus u over 1 minus u. That seems nice. And then, of course, I can place that up there. But if I place that up here, a power of 1/2 means I have a square root. And don't forget your plus c. Okay, well, this seems pretty good so far. We have to remember that u is equal to the sine of theta, right? So u is equal to the sine of theta. So we're just going to back sub, right? So sine of theta is going to go here and here, and we're going to work through some identity work. Okay, so I've got 1 plus the sine of theta. I've got 1 minus the sine of theta plus c. And I'm thinking about where we need to land. It'd be ideal to land at maybe secant of theta plus tangent of theta, or tangent of theta plus secant of theta inside. So we need to work towards that. Well, let's think about this. If we multiply the top and the bottom by 1 plus sine of theta, when you multiply, the denominator is going to give you 1 minus sine squared, and a Pythagorean identity will lead us towards cosine squared. Let's try that and see what happens. I think that'll be a little bit clearer. Okay, so here we go. So multiplying the top and the bottom, the numerator and the denominator, by 1 plus sine of theta over itself, right? So that's a useful form of 1. So that seems pretty nice. And so if I multiply, keeping that square root in mind, it'd probably be nice, don't forget your absolute value bar like I did. With that square root in mind, it'd probably be nice if we kept the square up top. That might play nicely in a little bit. So I've got, looks like 1 plus sine of theta quantity squared, this times this. And then downstairs, that's going to give me 1 minus sine squared, right? That's the product of conjugates, so I'm going to get a squared minus b squared. But by Pythagorean identity, that's exactly cosine squared of theta. And that's nice because I can take the square root. And so now I've got the ln of the absolute value of 1 plus sine of theta over cosine of theta when I take the square root. And then I can just break that up into 2 fractions, right? So I can call that 1 over cosine of theta, and then sine of theta over cosine of theta. Yeah, so this one is very satisfying. So we're directly computing. We can see the end result makes sense. And we're left with the ln of absolute secant of theta plus tangent of theta plus c. So I really, really like that one. It turns out if you're careful, you can use that technique on any odd power of secant, depending how patient you are, because I think with every odd power, you're going to end up with more and more linear. I think you're going to end up with 2 more linear factors. I have to think about that. But yeah, it is an exercise in patience, so you might want to try to do this technique with the integral of secant cubed. The typical way to solve for the integral of secant cubed is to, I think, use integration by parts and then solve for the integral. But I'm going to give you homework, channel. So homework. Be interested to see if anyone does this. And then can you come up with a formula for secant of, let's say, 2n minus 1 theta d theta. So secant to odd powers. And let's say n is a natural number. Okay, so as promised, we're gonna do 3 of these integrals of secant. So we did 2 of them so far. The first one was kind of it was okay. The second one was fantastically fun, and let's check out this third one. Now the third one relates to a video I talked about a long time ago. So before I talked about rational parameterization of the unit circle and of Weierstrass substitution, check out that video because now we're going to apply that. So our Weierstrass substitution and so we let t equal the tangent of theta over 2. And from this, so you can do a bunch of work with triangles and algebra and get all these results. Not terribly bad. So sine would be 2t over 1 plus t squared. Cosine of theta would be 1 minus t squared over 1 plus t squared. If you solve that for theta, And then you take the derivative of both sides, so you're going to have to take the derivative of arctan. So d theta is equal to 2 over 1 plus tan squared dt. Maybe I should put a condition on theta. So for theta between negative pi and pi. Okay, so let's use this Weierstrass substitution to try to integrate secant of theta. Okay, so yeah, let's go for it. So we're actually going to start out in the same way as the last problem. So we're going to call secant of theta 1 over cosine of theta. And again, we want to remember that cosine of theta is equal to 1 minus t squared over 1 plus t squared. And then we want to remember that d theta is equal to 2 over 1 plus t squared dt. Okay, so 1 over cosine, that just means the reciprocal of cosine, so just flip this. So I've got 1 plus t squared over 1 minus t squared. And d theta is exactly this. So d theta is 2 over 1 plus t squared d theta. We have some canceling, and we can do some partial fractions. So the partial fraction decomp work is similar to the last problem we did. I'm going to leave that to you as an exercise. When you do the partial, so try partial fractions. Like, it's so similar to the last one, I feel comfortable just going from here to here. So try partial fraction decomposition. Okay, if you do that, you get the following. So you're going to get 1 over 1 minus t plus 1 over 1 plus t. You can easily convince yourself that's that, right? Because if I add these, it's this product plus this product, there's your 2, over this product, which is exactly this. And that's dt. So that's not bad to integrate. Again, we did that before. So that's minus ln of absolute 1 minus t plus the ln of absolute 1 plus t. That's plus c. And we're going to remember something from our Weierstrass substitution in just a moment. Let's just rewrite this. So again, we'll skip a step because there's so much similar work compared to the last one. But we know that we've got the difference of log, so it'll be the log of this over the log of this. Okay, so there. So that seems pretty good so far. So recalling from our Weierstrass substitution, remember that t is equal to that tangent of a half angle? Let's use that. Okay, so yeah, that's going in for t. So going in for t, this gives me the following. So I've got the ln of absolute 1 plus the tangent of theta over 2 over 1 minus the tangent of theta over 2 plus c. Well, in the previous video, we proved a trig identity regarding the tangent of theta over 2. So by the previous video, check that out by the way, by the previous video, we've got this is equal to sine of theta over 1 plus cosine of theta. Okay, so this equals this by our previous video. And downstairs, more of the same right here, right? So we've got 1 minus sine of theta over 1 plus the cosine of theta plus c. Okay, we can do a little bit of fraction work here. Put that over 1, put that over 1. And so to add fractions, I mentioned before, I like to do it in this way. So a over b plus or minus c over d. Again, assume b and d are non-zero. That's exactly AD plus or minus whatever sign you have. CD, oh, CB. So AD plus or minus BC, or CB. There we go, CB, that's a B. Over BD. So product plus or minus product over product. Okay, so if I do that here, let's see what we get here. So this product is 1 plus cosine of theta plus this product is sine of theta. So that's going to give me 1 plus cosine of theta plus sine of theta. And then downstairs more of the same, right? So to subtract, it's product minus product over product. So that's 1 plus the cosine of theta minus the sine of theta. They're both over the same thing, so that'll cancel, right? The 1 plus cosine will cancel from here and cancel from here. If you didn't like that, feel free to multiply the top and the bottom by 1 plus cosine of theta. That's fine as well. It's the same thing. Okay, so from here, we're trying to arrive at a statement involving tangents and secants, right? Statement involving tangents and secants. Let me quickly just rewrite this. Actually, this is fine. Okay, so we want to introduce tangent and secant. So let's multiply the top and the bottom by 1 over cosine of theta. That'll introduce tangents and secants. That's where I want to land. Okay, so let's see what we have now. So we've got the natural log of, so yeah, just distributing, being careful here. So this product is secant of theta, right? 1 over cosine of theta is secant of theta. This product is 1. This product is tangent of theta. And then downstairs, so this product is secant of theta. So this times this. This product is 1. And this is going to be a, looks like a minus tangent of theta. Okay, so in the previous video, I gave what I called a sneak sneak behind the curtain, or a peek behind the curtain, or a look behind the curtain, and sort of gave my thinking on how I went from here to our final result. In fact, here's where we're going to apply that. So let's check that out. And remember, in the previous video, the key realization was that this quantity here and this quantity here, they were reciprocals. And sort of to aid your thinking in that, just remember that tangent squared of alpha plus 1 is equal to secant squared of alpha. Just subtract tangent from both sides, you get that secant squared of alpha minus tangent squared of alpha is equal to 1. And then you can just factor that as the difference of squares, right? You can call that secant of alpha plus tangent of alpha times the conjugate, right? Secant of alpha minus tangent of alpha. And so that told me that these are reciprocals of each other. Their product is 1. And so here we were kind of clever. And the idea was we're going to multiply the top and the bottom by secant of theta plus tangent of theta. And the reason why we do that is we can use this nice reciprocal property. You can definitely check out that last video. You can see all the gory details. Okay, so yeah, we're multiplying by secant of theta plus tangent of theta over secant of theta plus tangent of theta. So we're essentially multiplying by a useful form of 1. Now for the numerators, I'm going to leave this alone. I'm going to leave this nice and factored. I'm just going to multiply out the denominators. So as promised, keeping this nice and factored, up top gives me the following. And then downstairs, I'm going to think about grouping these together. So now I'm going to multiply, distribute in this way. So this times this should be 1 because we said they're exactly reciprocals, so that's 1. And then this times 1 should be secant of theta plus tangent of theta. But these cancel, and we get that classic result. So I enjoyed that one as well as the second one. Very satisfying. That Weierstrass substitution is nice. So yeah, check out the last video on the trig identities that we used here. That's really nice. But also check out the rational parameterization of the unit circle video where we introduced the Weierstrass substitution. With that said, thanks for watching, everybody. I'll see you real soon.